Hello everyone. In this video we are going to talk about one of the graph search algorithms, which is also used for path planning, and this is one of the most well-known and mostly used algorithms in the literature, called the A-star algorithm. The good properties about it is a complete algorithm, which means it can find the solution and all of the solutions in a limited time, and if there is no solution, it can tell you that, hey, there is no solution. And it is optimal, which means if there are different paths that you can find from start to goal, then this one is going to return the shortest one, provided that the function, the cost function we are using, especially a part of it, which we call the heuristic part, is a special type of function which we call admissible, or you can also say if it's consistent. So what are these? I'm going to explain. But what this one is an informed search algorithm. So it's not just going to keep looking in the dark until finally find something, right? So if you remember from the PRM method, what you really did, you created a bunch of random points in the grid and then try to connect them together and then make one connected graph, and such that it involves the initial and the final point, and then find the path. Okay, so by no means it was complete, and by no means it was optimal, correct? So it was what we call resolution complete. So if you make your resolution, or the number of nodes, large, ultimately you are going to find a solution. But is that optimal? Most probably not, unless you do lots of extra stuff on it, smoothing of the path and so on and so forth. And you probably also generate those random data points with a little bit smarter way than just uniformly distribute them all over the place. So now, what is this function? So this function has two parts, a g and h. So your cost function that you are trying to minimize, and it's the cost going from one point to the next point, has two subfunctions, g and h. G is the cost that you calculate from the start point to the current location. And h is kind of the remaining of it, right? The cost to go from your current location to the goal. So you break the total cost for going from start to the goal at each location. When you try to calculate it, you break it into two parts. How much does it cost me to come from start to here? You call it G. And how much it costs me to go from here to the goal? You call it H. Now, G comes from the weights that you apply to the edges of the graph, and there are different methods that you can do. One of the simple ones could be like a travel distance, right? The length of the edge could be an easy choice for it. And the heuristic function, as you know, the word heuristic means kind of rule of thumb, right? Case by case dependence, right? It's not like there is a general rule for determining h. Now, h has to have some properties if you want an optimal solution, but there is not one single general rule that I can tell you, and based on that you can choose your h. There are different types of h. It can depend on the problem. For some problems you change it to achieve faster convergence and better results, right? So it's kind of a rule of thumb. That's what heuristic means. Okay, now we'll talk about what properties h has to have to give you optimal performance. So first of all, as I said, this method is complete. Complete means, as I said, it can find the solution if it exists in a finite time. If there are more than one solution, it's find all of them. And if there is no solution, it will tell you. But it can do it as long as the weights on the edges are all positive and the number of edges are not infinite. Okay, so a finite graph, you should not have infinitely many edges, many lines between the nodes, and the weights of those nodes which form, total of them will form this function g of x. So if you look at this graph, the weights on the nodes, it can be the length of them or it can be any other thing, correct? Depending on your application. Then these guys should all be positive and there should be a finite number of them, okay? If those conditions are there, then this method is complete, which for most of the applications, of course, these two are the case, unless we really want to apply a negative weight to the edge, which means the cost drops when you travel, which is kind of counterintuitive. The other thing is the computation time of it, the complexity of it, not time of it. The complexity of it is exponential. So maybe it's not a good thing to say we call it the complexity of it is exponential, which means as you have more and more nodes, the time or the number of operation it takes for this algorithm to find the solution is going to be like exponential of that, or a power function basically, correct? So let's say if your number of nodes goes from 2 to 4, then the number of operations you have to calculate is not going to be just 2 times more, it's going to be e to the 2, which is like 8 times more or something, right? So it is going to grow into very, very large number of operations as the number of nodes basically increases. Now, the other thing is the complexity of this quite largely depend on the function h. Some functions of h, they have something called the branching factor. I don't want to get into super depth of this algorithm. I just want to introduce it to you. So the branching factor is a factor which determines how far this h helps your algorithm either explore new branches or just keep going toward the goal more focused, okay? And which one of these branches that were previously open, it is going to prune them. Prune means it cut them. It says they are closed, they are dead end. I'm not going to explore them anymore. So I'll show you what explore mean, what close mean. But basically, if it means how much exploration, how much going around into the workspace to find a path to the goal position this h is going to cause. Okay, the more it forces you to look all over the place for an answer, the more time it takes. But the faster this says, hey, this branch doesn't look like it's going anywhere, I'm going to cut it and keep going in the remaining promising branches. Okay, that might make it faster. Another definition that we have for h, or one of the properties that we have for h, is called a monotone or consistent function. And that is when h at node x is less than or equal the d between x and y and h at y. So x and y are two nodes here. dxy is the weight of the edge, or the edge distance between the two nodes. So if h at x is less than or equal h at y plus the distance that you traveled from, plus the weight of the edge that you took to travel from x to y, then you can call that h function a consistent or monotone. So what do I mean by that? Well, if you look here into this graph, as I said, these numbers in black that you see on the top of each edge, these are those dx and y. And then also below each node, there is an h value. There is the value of the heuristic function. So the red ones are heuristic. So now, for example, when I go from, let's say, B to E, or E to D, the h here at x, so this is like my x, this is like my y. The h here at x is 5. The h here at y is 14, and the dxy is 11. So if this h at x is less than the weight of the edge plus hy, then I'm good. And clearly it is. Here 5 is less than or equal 11 plus 14. Now you might say, what if I switch the order? What if I go from B to E? Then what? If I go from B to E, then I switch the location between X and Y. And here I set this X, this Y, and I go this way. And now it is going to be 11 is less than or equal 5 plus 14, right? No, 14, I'm sorry. 14 is 14, h at x is less than or equal 11, and then plus 5. And you see that's the case here. So it doesn't matter which direction I go, especially when I go from this direction, from B to E, because I start here at A and want to end at Z. So the closer I get toward the goal, my H values drop, because if you remember, H means the cost to go from your current location to the goal. And here is the goal, and here is your start. So I expect my H values as I get closer and closer to the goal to what? To drop. And I expect at the goal, my H value here is what? Is 0, because there is nowhere else to go after that. That's where I want to end up. So the H at the goal should ideally be what? 0. So you see, that's the case here, and that's what makes, for example, I have to check it for each and every one of these. If for each and every one of this condition is valid, then I'm good. So you see, for example, I checked it for nodes B and E. Now, if I check it for other nodes, for example, from A to D, right? 21 is less than 5 plus 18, 7 plus 18, so I'm good. If I go from A to C, again, 21 is less than 4 plus 18, that's right, so I'm good. If I go from here to here, 21 is less than 9 plus 14, so I'm good. This one I checked. Let's go from 5 to here. 5 is clearly less than 7, so I'm good. If you go from F to that, 8 is less than 9, because this one is 0, so I'm good. If I go from here to here, 18 is less than 14 plus 8, that's good too. 2 more nodes. 18 is less than 22, that's good. And finally, 18 is less than 20, so that's good. So you clearly see the H values, whatever H function was, the H values that it gave me for each node is going to make H here what? A consistent or monotone function, okay? So the H values are only assigned to what? To the nodes, but the D values are assigned to what? To the edges. Okay, so clearly in this case, it is a monotone or consistent function, right? Good. Now, we talked about completeness. We said finite graph with non-negative edges, that makes it complete, but we also said optimal, which means the minimal actual cost that is possible. So when is it that I can expect A star to return an optimal, a minimal solution, in this case for me, for F? It says if H, the heuristic function that you choose, is an admissible function. What does that mean? Means it never overestimates the actual cost to get to the goal. Okay? Well, yeah, that looks nice, but it's a little bit hard to mathematically show, right? Because I don't know my actual cost to the goal. So how can I assure that whatever function I choose never overestimate that? So this admissible function definition is rather hard to use, right? It's a nice definition, but it's not so useful. But you can show that if your H function is consistent and the value of it at the goal location is 0, then it is what? Admissible. So when can I assure optimality? When H is consistent, like we just checked it was, and H at the goal was what? 0. So for this case, if we run A star, it should definitely return what? An optimal solution, and we'll see that. Okay, so this admissible definition, again, it's a nice definition, but it is not so practical. we better go with the fact that, say, if it's consistent h and at the goal is 0, then it means optimality. Good. Now you might say, okay, with all that, what kind of function can I choose for h? Right? What kind of function can I choose for h? What type of function? Well, there are different functions, there are different methods that could tell you some general guidance for how to choose h. But one of the functions that can help in many path planning algorithms is just the Euclidean distance, right? Just the Euclidean distance. So basically, if you are at one location and you want to go to another location, all you need is basically the Euclidean distance, which is clearly the square root of delta x squared plus what? Delta y squared, right? Let me put this back and do a little bit of cleaning. So here, right? If I'm at node 1 or node A and I want to go to node B, clearly this is what? This is xa minus xb squared and then plus what? Ya minus yb squared. Another one that you have is called the Manhattan or Taxicab distance. So some people also call this the taxicab. Okay, the taxicab distance also, or Manhattan distance, or some people call it L1 norm. So this taxicab or L norm or Manhattan distance, what is this? This is basically the summation of the difference between the x's and the difference between the y's. So it is like x, or actually in this case, it's just simple. I don't even need a summation because I only have two numbers in my array. So it's just xa minus xb, absolute value of that, and then plus ya minus yb. Basically, this method, since it's a grid search, if you have a grid, all you can do at each point to go one cell to the left, right, up, and down. So when you are here, you cannot move diagonally. This motion is not allowed. So if you want to go from that red point, let's say, to this green point here, what you can do is to move basically two cells, correct? 1, 2, and 3 cells to the right, and then from there 2 cells upward. So there's going to be 2 plus 3, which is 5. Okay, so a diagonal is not allowed. If you could go diagonal, then you would go in 3 steps: 1, 2 diagonal, and then 1 to the right. Okay, or 1 to the right and then 2 diagonals. So when the diagonal motion is not allowed, you can only move left, right, up, and down in the grid search algorithms like this. When your workspace is divided into a grid, then you can use this Manhattan distance. If you're allowed to go straight line and you are not bound to move on a grid, then this guy could be a good use, okay? But as I said, for most of our algorithm, we discretize the workspace into a grid, and then we move from one point of the grid to the next to the next. So for many applications, this Manhattan distance, okay, or L1 norm is good. Euclidean, you call it the L2 norm. Okay, this is the L1 norm. There are other norms for vectors that you can use. In general, if you have a vector with n components called vector A and another component called vector B, what you need is to subtract each component in A from the corresponding in B, take an absolute value, and then sum all of these absolute values together. So in general, it is like a summation of like XA, or you can call it like XIA minus XIB, the absolute value of that, and I goes from 1 to n. Okay, so here you have n components, nx components in vector A and vector B. That's in general what the Manhattan distance is. There are other distances too. You probably hear and see in other parts of the literature, like the Hanning distance and so on, the number of misplaced tiles, what we call. But these are some of the obvious choices. And you know definitely that, for example, if you use this L2 norm, it would absolutely can match this criterion for you, especially when this D, the weight of the edge, also comes from the distance that you traveled along the edge. So if you have chosen this D to be the distance along the edge, the actual distance, then definitely you know in Euclidean space, if you want to go from point 1 to point 3, and if you go straight, this L13 is definitely less than or equal what? L12 plus L23, correct? Always the straight path is the shortest distance. It's one side of triangle is always less than the sum of the two other sides, right? So in Euclidean space, if D and H are determined that way, you are guaranteed to have an H that is consistent, okay? So just wanted you to know a little bit about some possible choices, but again, these are not the only choices you have for H. As I said, H is heuristic, so in some examples, one function might work a lot better than the other one, or you might even find a function that is none of these distances and it outperforms, okay, because it's depending on the type of the problem to be solved. One other thing I mentioned, and then we get into the explanation of the algorithm and solving a couple of problems. There is an algorithm in the literature that you can see. It's called the Dijkstra here. Okay, so the spelling of that, as far as I checked, the way that you pronounce it, it is called Dijkstra. So this J, as far as I checked, it's not pronounced, and it's called Dijkstra's algorithm. It's a pioneer to A star, and it's the same as the A star as long as you forget about H. So all the cost function you are trying to minimize in Dijkstra is G, basically. The total distance, the total weight of the edges, or the distance that you came from start to here. That's all you're trying to minimize, right? If I'm coming to a node, I want to have it the short distance. The bad thing is it doesn't look forward. It only looks back. It only looks how far I have come to this point. It doesn't look how far I need to go from here to the goal. So you might go down a path that looks quite promising because it is a short distance, but since you are not looking forward and not looking where you're going, then as you try to expand that node and move forward, you see, yeah, so far it was so good, but now from this point on, it's not. It is going to give me some big H values, and the path from here on to the goal is actually a very bad path, right? And so I better stop. It's like when you are in the traffic lines, right? In the street. So, right, sometimes you don't look too much forward and you change a lane in hope that maybe this line is looking what? Faster because there are fewer cars in it, and you jump to that lane from your busy lane. Say, yeah, that lane has a lot less cars, I'm gonna move forward. But then when you go a little bit forward in that lane, you see, oh, there is a traffic accident right there. And that's why not too many cars there, because they have to now wait for the cars in the other lane to pass, even though slowly, and maybe give them a way to basically merge in. So you always need to, when you are doing path planning, you need to look behind you and look forward. That's why this method A star is way more intelligent than Dijkstra, and for many applications it outperforms it. It performs a lot faster than the Dijkstra. So Dijkstra is a special case of A star when H is considered 0. Good. So these are important properties of A star that I wanted to talk about. Now let's see how this method works, and we'll go work on that through a couple of examples. Right, so this one I found on Wikipedia, and this one I found also by a Google search. These are some simple examples. We are going to go here from start point to the goal point, and here we're going to go from node A to node Z, and we are going to find the optimal path with the minimum cost. So there are some terminologies that you also might hear when you're working with this algorithm: current node, visited node, a closed branch, and open or active branch. Okay, so what is it? Let me explain them as I go through solving these examples. Let me explain the algorithm by going through example instead of me just reading over them and then try to refer you back when I'm solving these, right, to those definitions. Let's go try to solve it, and then whenever we reach to one of these, I explain. Okay, so, but the major goal of this algorithm is this: find a node and expand the branch under a node which has what? Which has minimum cost function, minimum f. If you see that branch with a node that is giving you minimal f value, that's your promising node and branch. Go ahead and explore that first before exploring everything else. That's why we call it informed search, right? It says don't give the same chance to all of the branches. Go in a branch that has minimal f value, right? And how do I know a minimal f value? A big portion of it is this heuristic. This helps me find which one leads to the goal faster with minimal cost. Okay, so let's solve these problems one by one. First, I go over this one. So my start location is A. So let's start with A. Let me get this down below so that I can explain on the right side. So here we start with node A. From A, all I can do is to go to B, C, and D. So I draw 3 branches, B to C, D. So each one of them is called a node. Each one of these is called a branch or an edge right now. It's just one edge, but as you continue that, it becomes like a branch. So now, how much does it cost to go from A to B, C, or D? Here, not only I have to add the weight of what? Not only I have to add the weight of the edge that connects A to B or A to C or A to D, I also have to add that value to the H value at those nodes. Okay, so I have to add these two together, I have to add these two together, and I have to add these two together to get the cost of going from your start point to B, C, or D. So if you see here, the cost to go to B is 9 plus 14, which is 23. We can write it down below B somewhere. Then, or to the left of it, right of it, wherever you want. Then the cost to go to C is 4 plus 18, which is 22. And to D is 5 plus 18, which is 25. You see, these are the costs of f of x at locations B, C, and D. Now, which one looks promising? C is the one that you should first go to because it has the minimal number among these 3 numbers. So now I say, well, let me go this path first. Okay, now I am at C. I can only go from C to E and F. So I expand C to what? To E and F. Okay, so the fact that I go from C to E or F, we call expanding the node, right? We are expanding this node, expanding this branch, not node, the branch. And since none of these 4 branches that you see right now lead to a goal location Z, or we haven't closed them yet, I'll tell you when we close them, then we call all of these branches A to B, A to D, A to CE, and A to CF, we call all of these guys what? Active or open branches. What is your current node? Your current node was node C, but now it is going to be what? E or F. So previously it was C, but now one time the current node becomes E, the next time it becomes what? F, okay? So, good. how much is the cost to E? Now, when you want to go to E, how would you calculate the number? So here you're going from A to C and C to E. So what you need to do is to add the weights of the edges along the way, which is 4 and 17. You have these numbers to add together to get your what? G at location E. And then what? Now, since your current node is E, what you need to add to it is what? The weight at E. So this is your H of X. So basically you have to add all these three numbers together to get F at E, which is 4 plus 17 plus 5, and it is going to be 26. So I'm going to write it down, right? And it is this path. The next path I have is go from A to C to F, this path. And again, I need to add the weight of the edges from A to F, which is 4 and 12, that's 16, and then add to the H at it, which is 8, 16, and 8 is 24. So now I am at 24 at F. Good. So this is how I expanded these two branches. Good. Now where do we go? Now we have to go and look at the F values of the end nodes. The end nodes are B, E, F, and D. These are my end nodes, right? By the way, I have gone through C already, so I passed C. C is already expanded and A is expanded. So if I want to write it down, I can say which nodes have I visited. It's node A with the cost of 20. Node A itself has only 21 because there is no edge before that, and C has a cost of 20. How much? 22. So these are visited nodes. Good. Now what? Again, look at these four end nodes. Which one has the lowest cost? Clearly that's B, right? 23, 6, 4, and 5. B looks the most promising. So here you have to pay attention. Although you came two edges, you might say, well, that's not fair. Here A to B is only one edge. A to E and F is two edges. That's why these numbers are bigger than 23. Fine, but maybe that's the difference between what? Dijkstra and A star. Maybe this A to B costed quite a bit, but now when I try to go from B to Z, it doesn't cost as much as I go from what? E and F to Z. So although here I might travel more edges from B to Z than E and F, but maybe those edges cost less than these guys. So at the end of the day, that path will cost me less than these ones that used to be promising. Now this looks the most promising, so let's go that direction, okay? Don't have any bias. Just because you expanded something a little bit further, it means that's the best one. Absolutely not, okay? Now let's do it. So B leads to what? B leads to what? A back and again E. Well, B, if I go back to A, first of all, A is a start point, right? And if I go back to A again, it is going to cost me 9 plus 14 to go from A back to A, which is 23, while the weight at A without anything else, if you just start at it, was 21. So if I go from A back to B and then go back to A, that already cost me 23 more than the 21 it used to have. So of course I cannot go back from B to A, right? That's a no-brainer. It's not going to go anywhere. The only thing I can go from B is to E. That's what I can do. Go from B to E. Now if I go from B to E, how much would that cost? So here, I'll try to calculate that cost and show it on the left side of E, and then we decide which one is good. So before that, let me do a little bit of cleanup so we can see everything nicely. So my goal is now, instead of going ACE, I want to go this path. How much is the cost? It's 9 plus 11, the total edge is 20, and then what? Plus 5. So the cost of going from A to B to E is what? 25. Now, which one is good? I used to have a 26, now I do have a 25. What does that mean? It means this branch here that led to E and costed me more than what I have right now, this branch is a what? Is a dead branch. Right? Because it cost me more. If I have something that costs me more, why should I even go in that direction? Right? That's completely meaningless. So what I will do, I replace that with this branch A, B to E, and that A, C to E, I say that branch is what? That branch is called closed. So ACE is a closed branch. Okay, so now you see the meaning. Branch is closed, node is visited, the current node that you are expanding, and so on and so forth. Right? Good. Now what? Now where do you go? So now the endpoints, if you look at them, are E again, F, and D. Which one could you go? Well, here there is a tie between E and D, but F is less than both of them. So clearly you have to start with F, right? Because F looks the minimal. So first I'm going to attack F. From F, where can I go? I can go back to C, which is definitely not a good idea because C is already visited. And if I go back, that costs me 4 plus 12 plus 18, correct? So I go to F, that's 16. Go back to C, that's another 12 actually. 16 plus 12, that's 28. And then plus 18, that's 46, which is way more than 22. So going back is not a option that you even want to consider. Now from F, you can either go back to D or go to what? Go to the Z. By the way, it's a good idea to show the direction of these arrows. Right? If I go back to D, what happens? So I go A to F to D. Well, you have 4 plus 12 plus 14 plus 18, which is a huge number, right? It is going to be like 48, way more than 24. So absolutely not. I'm not going to go back to D, okay? So it doesn't even worth it going back to D. Absolutely not. If you want, we can do it. And then, since this guy is, as I said, going to cost 48, clearly that's not a good idea. So this is what? This is a dead branch. You're absolutely not going to go there, A, F, and then from F to D, right? So going from A to F to D is absolutely not something you want to proceed. Now, you go A to C to F to Z. How much would that cost? So A to what? C, F, Z, this path. How much? It's 4 plus 12 plus 9, and here, if you remember, H here is 0. So the total cost is what? 25, correct? And at this point, guess what? You reach the goal location. And since you reach the goal location, really, that means you can terminate the algorithm, okay? Plus, when is it that you might explore the other branches? Because there is another branch. There is a branch from E to Z as well. There is this branch going from E to Z. That's the only branch that is still active. Am I going to pursue that? Well, I don't have to, because here this weight is already the same as that one. Okay, so by adding one more edge, there is no way I can end up with a number smaller than this unless here the weight of this edge is 0, and guess what? The weight of this edge is not 0. Okay, so although this E drops to this E, this H drops to that H, but if you calculate it, you'll see the number is going to be what? If I want to go A, B, E, Z, the cost is going to be 9 plus 11 plus 7, that's 27 plus 0. So the cost of going in that direction is 27, which is never going to be less than 25. So that branch is not going to lead to a number less than that. Therefore, I don't even need to, as I said, since this number is the same as that, not bigger, there is no value in expanding it. Unless this number was less than that, then I have to explore that branch as well, because it might end up with a smaller number. But since I'm already at the number, the best number I found, there is no reason to add one more edge, because the weight of these edges is typically not 0, right? They are typically bigger than 0. If you see there is an edge with the weight of 0 around Z, then yes, you expand that. But even if you do, still you're going to get the same number. So it gives you like 2 optimal solutions, and you just need one of them really. For the sake of completeness, yes, then you have to return both of them. But if you just care about finding one path, then you might just stop the algorithm right there. So that's all I need, and that means I am going to what? I'm going to stop it right here. And that's it. My goal, my best path is what? Is to go from basically A to C, and then what? To F and Z, and the maximum cost that I need to pay is 25, correct? So this is my best path, optimal path. Okay, that's how you solve this A star. Now, let me show you another example here. That's the same thing, kind of, but let's take a look at that. So here I'm starting at point S, and then I am going to go to G, right? So all I can do is to go to A and D. That's all I can do. Now here there are weight of the edges, but there should be also a value of H at nodes. At G, you know the H is 0. But at C, A, B, D, and E, there should be some H values, okay? So if we go with the same numbers at Wikipedia, these are the numbers, 4, 2, 4, and then 4.5 and 2, okay? These are the numbers suggested. Now, is the H function here is monotone? We can check that, right? To see whether it gives me an optimal path, although here there is not really more than 2 general paths, going in the DE direction or going in the ABC direction, right? So it's not really complicated. There is only 2 paths you have to decide. But if I want to see whether my H is monotone or not, so when I go, let's say from A to B, this number should be less than or equal sum of these 2, right? If you look here at the monotone condition, has to be less than or equal. So equal is still accepted. Okay, and this is equal to those, so I'm good. If I go from here to here, this 2 is less than 3 plus 4, so I'm good. Here I have to choose a value that is less than sum of these 2 and less than sum of these 2. And that's if I, for example, choose 5 for this start position, then 5 is less than 5.5 and less than 6.5. So that makes life easy for me. And if I go here, 4 is less than 4 plus 0, so still equal, that's good. 2 is less than 2 plus 0, that's good. 4.5 is less than 3 plus 2, I'm good. So H here is monotone. Okay, so I should be able to get a solution. And now again, I go from S to A. The cost is 1.5 plus 4, which is 5.5. And the cost going to D is 2 plus 4.5, so it is 6.5. Which one would you expand? A. So A becomes your current node. And from A, I can expand to B only. And now that you go from start to B, the numbers you have to add are 1.5 to the total edge plus the goal H, which is again 5.5, right? So you end up at 5.5. So your cost has not increased, which is quite interesting, right? No increase, because the H here is a good drop, really, right? But that's fine. So that's 5.5, still below 6.5. So I'm gonna continue with B and go from B to C now. Now, when you go from B to C, you have to add 1.5, 2, 3, and 4. Okay. So the numbers you're adding is gonna be 9, 10.5, correct? The number is 10.5. And look, although I have come 3 edges, the other branch I only came 1 edge. Now that this number exceeds the other number, I'm not going to continue C, although I have come a long way. I'm going to go back and expand D. Say, well, that's 6.5. Now this is the current node. From D, I can go to E. What's the cost going to E? Well, again, add all of the edges leading from start to E in that path, which is 2 and 3, and then the H at E. So you're gonna end up at 7. 7 clearly less than 10.5. So I keep going. And now, guess what? I can reach the goal. And if I reach the goal, you see the number is gonna be what? It is gonna be 2 plus 3 plus 2 plus the number here, which is simply 7. And clearly this one is better than that number, so I can what? Can already say this branch is a dead end. Because this branch, I reached the goal, my cost is less than the other branch already, so there is no way pursuing that branch and expanding it. So that is my good path, S to D, E to E, E to G, and the total cost is 7. Done. Okay, so that's how you look at an A star problem. Okay, so hopefully that was a good intro to A star for you. And now, before we finish this video, I want to show you a Matlab demo. So here is a code that one of my students wrote in the past. I'm going to run his code for you. And here we go. So it gives you a grid, and he just broke it down into 11 by 11. So each one of these is just one possible location you can step. It says use your left mouse button and mark down the goal location. So here, this is my goal location or target. And then it says use left mouse button as many times as you want to determine the obstacles, and then use right button to finish assigning the obstacles. So here we go. Let's say this is one obstacle like this. Then I have an obstacle like that. And then I have an obstacle like this. Right? And maybe even an obstacle like that here. Okay, so each one of them is a shape of an obstacle, right? This is like this is another shape, this is one. And let's say I'm done, I right click, right, at the end point. So here I have like 4 obstacles, and now let's say my start point is here, right? Wherever you want, let's say here. And look, boom, right? And I can repeat that as many times as I want. Let's run it one more time. So here is my goal, maybe. And then my let's see, my obstacles are here, 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 here. Then we have here, 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 here. We have good. So let's make it hard on it. And here we go. These are 4 obstacles, and this is my start point here. You see? So it works just fine, and it definitely finds the shortest path. So here it could go this way and then wander around and come all the way here, right? If I did that, let's see if I can insert lines for you. So I could go up here like this, and then I could go here, and then here, here, and if you continue all the way down to here, now here you clearly see it can go diagonal, okay? So if it can go diagonal, then I can do some better things. If I couldn't, if I had to go only basically from grid point to grid point without diagonal, then yes, this is what I could do, like this. Okay, which is clearly a larger distance, right? But if I could go diagonal, then instead of these guys, I could do something similar, right? Could go diagonal like this, go to that point, and here if I didn't make the right decision and I moved forward like that, then I had to come here, but then when I reached this point, I could go diagonal here like this, go down here, again I could do a shortcut, right? Something like that, and then this one. So clearly I could, or here maybe this one actually. If I made the wrong choice and I went into the direction of the black path, that is a little bit longer than this kind of orange path, right? Okay, so that returns the optimal solution, even if it's just like meaning 1 cell smaller, right? Yeah, I just counted them, and the number of cells traveled in the green, in the orange path is 15. For the black one is 20. So clearly it could get me the optimal solution here, and clearly here the Euclidean distance that was used, because you could travel diagonally, was efficient to solve the problem for you. Okay, so thank you so much for your attention, and I will see you in my next lecture.